So last video we introduced the Biot-Savart Law and took a look at the magnetic field due to a long straight wire. Now here the problem that I want you to consider is imagine that you have a circular arc of wire, and we will not stress out over the details about how exactly we are getting the charges on and off the wire while we're carrying the current. So let's say we're carrying a current I, like so. The point of interest will be at the center of the center of curvature of the arc. So that would be about there somewhere. So the first thing I want you to do is tell me which way is the magnetic field going to point at this location. Yeah, it's going to point out of the screen. Again, put the thumb of the fingers of your right hand along the current. Your fingers will curl around in the direction of the magnetic field lines. Now here, it's not going to be like perfectly stacked circle. It is going to be circles, or circular-ish. That's not going to be the perfectly stacked circles or even a perfect circular shape like we had before, but the general sense still works. So the magnetic field points out. And now what I would like you to do, this is going to be another one of those pause the video moments. Let's say that the angle that our wire takes up is phi, and we want to do phi in radians here. What I want you to do is go ahead and apply the Biot-Savart law to this situation. So you'll want to dimension out your ds and your r hat and figure out how exactly you're going to want to set up your integral. And then hopefully what you will show is that at the center of the arc here, the magnetic field strength is mu naught I over 4 pi r phi, where phi is the angle that the wire took up in radians. So go ahead, pause the video, give that a try, and then we'll debrief on this. Okay, so let's go ahead and debrief on this. So again, the idea here, so we're going to look at a small differential chunk of wire, ds, and again, remember we point ds along with the current, and we will identify our unit vector that points in towards the center of the circle at that location, r hat. And we'll just say that this distance here is r. So we can go ahead and use the Biot-Savart law again here. So dB is equal to mu naught over 4 pi I ds cross r hat over r squared. Now here, our little r is also equal to this big R here, so that helps. And no matter where you are here, this is always going to be a right angle. So phi is going to, sorry, you shouldn't call this phi now. Let's call it alpha, let's say. So this angle here, though, is 90 degrees. So this means that we're going to have a sine of 90 here. So we can put this in. We'll have mu naught, so dB without the arrows, because remember we already figured out the direction with our by looking at how our fingers curl, but you can double check that by doing the cross product right now. So we'll have an I, a ds. Now when we do the cross r hat, this will be times the number 1 times the sine of 90 degrees, which is also 1. And then we'll put in big R for our distance there. So this looks like dB is, dB is mu naught over 4 pi I ds over r squared. Now, what's going to be left here is to figure out some convenient way to integrate this. And a change of variables is going to be helpful here. It'll be helpful to remember from the definition of angle, if this angle here is d phi, then ds is equal to r d phi. So let's go ahead and make that substitution. So this will be mu naught over 4 pi I r d phi over r squared, canceling 1 power of r. All right, so then we're just left to evaluate the integral. All right, I'll integrate this from 0 to b and get b. Okay, that was the hard part. Mu naught over 4 pi. And then we can pull out our constants. I and r are constants, and we are left with integrating d phi from 0 to phi. And please don't give me any stick about using the same letter here that I use here. Physicists do that all the time, and we are well aware that the integrating variable isn't the same variable as what you have at one end or the other. If it gives you some joy in life, you can call it d phi prime if you want or something like that, but I'm not going to do that. Anyway, this is certainly a lookable, uppable integral if you don't have it committed to memory already. It's just phi. So we get that b is equal to, here, let me write it down here. B is equal to mu naught over 4 pi I over r times phi, which was what was to be shown. Okay. And similarly, you can, with more advanced treatment, you can come up with relations. So this is purely at this center point right here, so it won't work anywhere else. But you can extend this idea and look at different different geometries of current carrying wire. So for instance, if we take this and extend it to be a ring of charge, sorry, a ring of current. So here, basically, just you get yourself a circular wire, and you can get yourself not too stressed out about how you attach it to the battery, but it'll work out okay. So let's say it's carrying a current counterclockwise. Again, here, the magnetic field at the center of the wire would point out, and your angle here would be 2 pi. So so here then, B would be mu naught over 4 pi I over r times 2 pi. And you cancel the 2 and the pi, and you're left with just a 2 in the denominator. So be careful. This equation looks an awful lot like the long straight wire, except there's no pi in the denominator. And it's only valid at the dead center of the ring of charge. And if you were to try to draw this edge on, and this is going to look bad, and I'm really sorry. So this is an edge on view. Of our circular wire. And let's say that the current is coming out of the screen at the top and into the screen at the bottom. So to the front, it'll be going down, and behind the screen, it'll be going up to complete the circle around. In a case like that, the magnetic field in the immediate vicinity of the wire is going to look pretty circular E. So it'll be something like that. And again, you can use your right hand, putting the thumb along the current and seeing how your fingers curl, what I sometimes call the hitchhiker rule, to verify the directions. And then as you get further out, they quit being perfect circles, but something like this. So the magnetic field lines get packed in, out of necessity, get packed in kind of tight inside the ring. And then outside the ring, the field is kind of weak. Another arrangement is a thing called a solenoid. A solenoid is just a whole bunch of coils of wire stacked together. In practice, what you do is you just make a coil. You get yourself any kind of circular, or cylindrical form. Say, paper, the cardboard tube from a paper towel even. And you just wrap wire around and around and around and around it for its whole length. I am going to schematically indicate that sort of like this, where each of these is a churn of wire. Now, when you do this, you do want the churns of wire to be pretty closely packed. When you do it in reality, the wire will be angled a little bit just because you're spiraling, but that angle doesn't matter worth a whole heck of a lot, so we usually just idealize it out like this. All right, so again, the same idea here. Let's say that for every churn of wire coming out, churn of wire, the current is coming out the screen at the top, and it's coming into the screen at the bottom, like so. So what you'll do is, when you figure this out, is you actually just add up these contributions from each and every ring individually and apply superposition. When you do that, what you get is that inside the solenoid, except right at the very edges, the magnetic field lines are actually quite straight. And this often, in the limit of the coil being very long, it does indeed become completely straight. And then what happens is the field outside the solenoid is actually fairly weak. Especially in comparison to what's inside the solenoid. So something like that. So this is a system that we will be taking a look at in the next video when we look at Ampere's law. One thing that I will finish up with, though, here is our magnetic dipoles. Oops. So in analogy, so remember we said that magnetism is sort of unique in that all the fields are due to dipoles, and that we don't have any isolated magnetic charges. So if we follow this thought around here, let's imagine we've got current, and this is supposed to be the plane perpendicular to the screen here. We've got current in a plane perpendicular to the screen. Let's say it's going around like this. Again, if you place your thumb along the current and you follow it along, you'll find that inside the coil, inside the loop here, the magnetic field is pointing up. And that is what gives us our sense of the direction of the magnetic dipole moment, which also gets called mu, not to be confused with mu naught. These are different quantities. So the magnitude of mu turns out to be equal to the current carried by the loop times the area enclosed by the loop. It's beyond the scope of this treatment to prove it, so I'm just going to state it. And you can show that, say, if you are along, say, some point right here on axis, and let's say that you are a distance z from the plane containing the loop, on axis you have the exact same kind of relationship that we've already seen. The magnetic field due to our magnetic dipole, will be equal to mu naught over 4 pi times 2 mu over z cubed. And I want you to compare this with the equivalent expression if we'd had an electric dipole. For an electric dipole, remember we saw that the electric field due to a dipole on axis was 1 over 4 pi epsilon naught 2p over z cubed, whereas p was the electric dipole moment. So these relations have the exact same functional form. This is trickier to derive, so I'm just going to ask you to accept that it seems reasonable, since this is an electric dipole and we have a 2 and a moment and a z cubed. This is a magnetic dipole and we have a 2 and a moment and a z cubed, that this makes sense with this choice of magnetic dipole moment. Alrighty. In the next video, we will go ahead and introduce Ampere's law and use it to get the magnetic field strength for our solenoid. So see you over in that video.